Hey, it's Ashmeet. Welcome to the Scribbled Equation. If you're anything like me, prime numbers fascinate you. They are the fundamental building blocks of number theory, the very foundation of how we think about numbers, patterns, and structures. From ancient mathematics to modern-day cryptography, primes are at the core of everything. So what makes them so special? A prime number is an integer more than 1 which can only be divided by 1 and the number itself. No sneaky shortcuts, no divisors in between. Think of them as the loners of the number world, standing apart from every other number, each as unique as they come. But here is the challenge. How do you find these prime numbers, especially when the next one can be anywhere? Stick around, because today we are doing a deep dive and talking about 3 clever algorithms to hunt down these elusive numbers. And yes, we will be live coding them in Python, and let's see how quickly we can catch them all. Prime numbers are way more than mathematical oddities. They are like the DNA of the numbers, and they have a key connection with how we understand everything from factorization to some of the most deepest unsolved mysteries in mathematics. In fact, every single number can be broken down into a unique combination of primes, thanks to the fundamental theorem of arithmetic, lovingly also called as the prime factorization theorem. Every integer greater than 1 can be written uniquely as a product of prime numbers. So for example, 15 is 3 times 5, and for example 100 is 2 times 2 times 5 times 5. Every single number can be broken down in such a fashion. The primes, on the other hand, are only written as the product of 1 and the number itself. For example, 17 is just 1 times 17. And even now, they are at the center of some of the biggest mysteries in mathematics, like the Riemann hypothesis, which could help us understand how these prime numbers are sprinkled throughout that infinite number line. Solve the Riemann hypothesis, you win the Millennium Prize by the Clay Institute, which comes with a handy-dandy prize of $1 million. But primes just don't simply live in textbooks. They are hiding in plain sight, powering some of the most important technologies around us. Every time you swipe your credit card, it's prime numbers and their factorizations hard at play in the RSA encryption, which keeps everything from your bank account to your Netflix password safe. And with the rise of quantum computing, prime numbers are poised to even shake up the future of encryption as we know it. Now I know what you're thinking. If you go to large enough numbers, maybe they all can be built out of smaller primes thanks to the prime factorization theorem, and therefore maybe beyond a certain number, no more primes exist. That's a good thought, but it's not true. It was Euclid, yes, that same geometry guy, who back in 300 BC, in his monumental work Elements, proved that there exist infinitely many primes. They just don't know any bounds. Start at 2, then 3, on to 5, 7, go all the way up to 101, 1013, 1,000,003, the list just goes on and on and on. The largest known prime number to us is 2 to the power 82,589,933 minus 1. It's a number which has 24,862,048 digits. And you can hang your hat on the fact that there are infinitely more primes that are larger than this prime for sure. These numbers may seem simple, and despite their importance, there is no clear formula or pattern to predict where the next prime will lie in the vast sea on the rail line. They just emerge unpredictably, and the only way to find them is through numerical algorithms, some statistics, and sheer determination. The deeper we dive into them, the more fascinating they become. There is just so much to talk about primes. I am already daydreaming about making more videos about them. But let me get back to the question at hand. Today we are asking the central question: what if you have to list all the prime numbers up to and including a certain number n? Say n is 30. Now that's easy to do. There is 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. Those are all the primes up until 30. But what if n is a million? Now that's not that easy to do, is it? But computational power and clever algorithms make it possible. We are diving into 3 algorithms, each faster than the last, to hunt down those prime numbers up to any limit that you choose. While they may not be the fastest ones out there, they certainly are some of the most widely used, and trust me, they are pretty quick. This first algorithm is what I call the brute force, and that's because it's simple, it's straightforward, and it sticks to the basics. So for every integer n less than equal to our upper limit capital N till which we want to find all the prime numbers, and more than equal to 2, we find its unique prime factorization thanks to the fundamental theorem of arithmetic. And then we simply count how many prime factors does n have. If it only has one prime factor, the number itself, then the number is prime and we add it to our list. Okay, so let's get started. Here is my Jupyter notebook where I will implement my Python code to find prime numbers less than equal to n. I will first get some powerful forces in Python, particularly the math package and the numpy package, which are going to come in handy. Now for the brute force algorithm, I want to begin by writing a function which takes in any integer n and it returns the list of its prime factors. This is guaranteed to us by the fundamental theorem of arithmetic. So I'm going to define a function, which I'm going to call factors, takes an integer n as the input, and it wants to return a list of the factors for this integer, initialize an empty list. We then iterate over all integers, starting from 2 all the way up to n, and let's remember Python's indexing for the range, n plus 1 means it will go up until n included. Once I am inside the loop, I want to check whether this integer k divides n or not. So I'm going to run a little while loop over here. So while n divides k, so the remainder when n divides k is 0. And we keep checking this condition as long as k divides n, because a given prime number can be a factor multiple times for a given integer. As long as it divides it with a 0 remainder, I'm going to add it to my factors list append my current integer k. Now once n has been divided by k, what is left is the divisor, n is n over k, and then you keep running this over and over again, and at the end you return from this function the factors list, and that's my function to return the factors list. Let's check this. So what if I run factors on let's say 15? I get 3 and 5 as expected. What if I do 100? I get 2, 2, 5, and 5. Sounds wonderful. What if I have a prime number, let's say 13? I just get 13. So it basically gives us all the prime factors other than 1, which build up that particular integer n. Now my second step is for my upper range, capital N. We want to basically run over every natural number, which is less than it, find its prime factors through my function factors. If the length of the factors list is only 1, it's prime, and we will therefore add it to our list. If not, we simply move on. So here I start by defining some n as an upper limit, and I define an empty list called primes, which are all the primes until the number n included. I will then run a loop over little n, which goes in range starting from 2 all the way up to capital N included. And I will check for the condition whether the length of the list of factors for the current little n, if it's 1, that means it's prime. If it's prime, I add it to my list of primes. And there you go. And this code is now ready. Okay, let's check it. So I'm going to ask it for the primes up until 30. What do you get? 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. Sounds great. The length or the number of primes up until 30 is 10. What if I go over to 100? There are 25 primes until 100. What about the 1000? 168 primes up until 1000. 10,000, It's taking a little bit of time to run now, but I get about 1229 primes until 10,000. Let's go even further, 100,000. And look at that, it's still running. It takes a while to run because brute force is literally going brute force. It's checking every single number up until n, and for that number it's checking how many prime factors does it have. It takes a while to run. Let's be a little patient here.
A few minutes later.
As you can see, it takes a long time to run. It's still not done. So giving us a sense that the brute force works, but it's not very efficient for large capital N's. Okay, so brute force was simple and was good for small n, but it got pretty slow as n became larger. Can we do better? Can we be smarter? Absolutely. I present to you algorithm 2, what I call as the prime focus. One can call it an optimized trial division method. To understand it, these 3 facts are going to come in handy. Number 1. A number n is prime if it has no prime factors less than n. Therefore, we only need to check if it is divisible by other prime numbers. Number 2. If n is not a prime number, having a factor r, then I can represent n as the product of r times s, where s is also a factor of the number n. If r is less than equal to square root n, it is guaranteed that s will be more than square root n. In other words, a non-prime must have factors and therefore also prime factors which are less than equal to square root n. So all you got to do is check the prime factors of a given number up to square root n. If there are none, the number is a prime. And finally, number 3. If we find even a single prime factor less than square root n, we know the number is non-prime and we don't need to check any further. We can abandon this number and move on to the next one. Okay, now on to building prime focus. Our first step is to define our capital N, the limit where we want to go till, and I'm going to use 30 as a placeholder for now. And we also define a list of primes, recognizing that 2 is a prime number that we already know. We're going to start here. Now I want to go over every odd numbered n and check if any of the primes in our current list, which are less than equal to square root n, are divisors of n. So let's have a loop for n in range, where I go from 3, the first odd number, all the way up to n included in steps of 2, so get all the odd numbers. I will have a counter which will check where I am in my primes list, which I'm going to call k. I will check whether my current prime number, which I'm looking into, whether if it is less than equal to square root n. So math.square root n, because that's all I have to check, as we've discussed in the algorithm. And then we look at whether this current prime number actually divides k, whether this prime number is a divisor for n. If it is, then n is not a prime number and we can break out of our current iteration, and we can then go on and check for the next prime number in our current list. We keep doing this over and over again, and if all the primes do not divide n, then our current m number is going to be prime. So I'm going to append it to my primes list, and there we go. We have our prime focus algorithm now ready. Let me now look at my list of primes for n until 30, and there you go, it comes out pretty straightforward. Let's look at the length of the number of primes. Of course, 10 primes until 30. What if I want to go up until 1,000? I run this very quickly. 168 primes until 1,000. What about 10,000? It runs very quickly. 1229 number of primes as expected. What about 100,000 now? This is where brute force was taking a long time. What about prime focus? So I run this for the main step. There you go, it ran. Fraction of a second, and I find out there are 9,592 primes up until 100,000. What about a million? Let's try it. So for a million, I run this. It's running, it's taking a few seconds. It ran just a couple seconds, and I find out there are 78,498 primes up until 1 million. Pretty cool, huh? And finally, for our third algorithm, I want to take you back to ancient Greece, where Eratosthenes was able to come up with this method, which is now famously called as the Sieve of Eratosthenes. And as the name suggests, it simply sieves out through a list of numbers 1 through n and marks out only the prime numbers. So for example, 1 is not a prime, 4 is not a prime, 6 is not a prime, 8 is not a prime, 9 is not a prime, so on and so forth. How does it do it? Let's find out. The idea is pretty clever. Start with this list of numbers from 1 to n, and then we systematically eliminate multiples of each prime starting from 2. So for each prime number n, we eliminate multiples of n starting from n square. So we have n square plus jn, where j represents the multiple number. So j goes from 0, 1, 2 all the way up, such that the multiple of n is less than our upper bound capital N. We start from n square because lower multiples have already been handled by lower prime numbers. By the end, the numbers which are still standing strong and unmarked, those are our prime numbers. This algorithm is highly efficient. It cuts down unnecessary checks as you go forward, and it works great for large n's. Let's implement this code and see how it works under the hood. Of size n is again a placeholder to be 30 to begin with. I'm going to define that list from 1 to n. I'm going to ask it the question, is it prime or not? And initially, I'm going to mark all the numbers as prime. And as the sieve will go through, it will start crossing off numbers which are not primes, and the numbers which stand as true at the end are going to be our prime numbers. We already know that 1 is not a prime number, so I'm going to assert that to be that it's not a prime. Again, notice Python's indexing from 0. So that's our first step. Next step, what I need to do is, I basically need to go over every single integer n less than square root n, and then mark all multiples of n which are more than n square to be non-primes. And again, why am I starting from n square in my marking? Think about this. When n is 2, we start marking multiples of 2, so like 4, 6, 8, 10, so on and so forth. When n is 3, we start marking multiples of 3, but from 3 square, which is 9, since 6, for example, has already been marked by the series of the prime numbers 2. For n equals 5, we start from 25, since every other smaller multiple, 10, 15, 20, has already been marked by smaller primes. So let's get started with this. I'm going to run a loop for n in range, starting from 2 all the way up to square root n. I'm going to the integer part of that, so math.square root of n included. So I'm going to add a +1 there. I'm going to check if the current number, is it prime or not? Again, being careful with Python's indexing of starting with 0. To see which multiple of n am I using beyond the n square, obviously, I'll have a counter called j, and I will check as long as n square plus j times n is less than equal to my upper limit capital N. In that case, the current multiple that I'm looking at is simply the same thing, n square plus j times n. And for this current multiple, I'm going to mark my isPrime array current multiple index -1, respecting Python's 0 indexing, and I'm going to mark it as false because all these multiples of the prime number n are not primes, obviously. And then I start going over to the next multiple, and I keep doing this over and over again, and this is how it will look like. Once I have run this, I need to basically define a list which will hold all the prime numbers. Then I will run through my list, k in range from 0 to n-1, so all the n numbers, and I will check if the isPrime array at the kth index, if the number still stands, if it's still not been marked out, it's a prime number, and to my list of primes, I'll simply append the current prime number k+1, and my code is ready. Until 30, I get my standard lists. What is the length? Should be 10. There you go. Let's go over to 1000. Let's run this. Runs very fast. 168 as expected. Over to 100,000. Sorry, 10,000 first. We get 1229 over to 100,000, runs very fast again, 9592, as we saw before with the prime focus, up to 1,000,000. Let's see how long it takes to run now. It runs, and a few seconds, there you go, 78,498 as expected. Now, of course, we want to find out how do their runtimes compare. We already have a sense that the brute force algorithm is going to get super slow as n becomes large, and prime focus and the Sieve of Eratosthenes are much more efficient. I ran some numerical tests where I changed capital N from 100 to 100,000, and I measured the time it takes for the algorithms to run. Here are my results. As we expected, prime focus and Eratosthenes beat brute force by orders of magnitude. Notice this plot is on a logarithmic scale. When we were searching for all primes up to 100,000, brute force took many hundred seconds, but the other two took only a few hundredths of a second. Before we wrap up, let's take a look at something rather cool, something called the prime periodic loops. Discovered by Omar Pohl and later adapted into this visualization by Jason Davies. Imagine plotting every number as a curve that intersects with its multiples. There is a periodic curve for 1 intersecting every number, then a curve for 2 which goes through 2, 4, 6 and so on. There is a curve for 3 which goes through multiples of 3, such as 6, 9, 12 and all the way out. Composite numbers get tangled up in many intersections. But primes? They are like the rebels, standing alone with just 2 intersections, their own and with the curve of unity. It's a stunning way to see just how different primes really are. It's a visual representation of how primes resist fitting neatly into the repetition structure of composite numbers. This visualization beautifully captures the unpredictable yet structured nature of prime numbers. Prime numbers, these tiny indivisible building blocks, are scattered throughout the number line like hidden gems. Yet their impact stretches far beyond the realms of abstract mathematics. From protecting the very security of our digital age to sparking deep questions about the very fundamental nature of numbers, primes are at the intersection of order and chaos, mystery and certainty. And yet, even after centuries of study, we still don't know how to predict the next prime or why they are spaced the way they are. Every discovery, every algorithm we build simply scratches the surface of this infinite puzzle. But maybe that's the beauty of it. Primes remind us that even in the most well-known systems, there is still room for the unexpected. This fascinating puzzle of the infinite primes is far from being over. We are just getting started. Thanks for watching, and I'll see you next time.